Hello everyone, welcome to OneClass. My name is Shanjida, and today I'll be going over some commonly asked chemistry questions, both at the high school/university and college levels. And I am currently a second year human biology student studying at U of T. And lastly, if anyone needs additional schoolwork help or needs tutoring, you guys could check the description box below. And with that being said, we'll get started. So our first question here says, what is the charge of the nitrate ion? And as if stated here that to calculate for the charge, we must know the Lewis structure of the ion and the formal charges of all the atoms in it. And so basically, to calculate the formal charge, we need to know the difference between the number of valence electrons and the electrons assigned to the atom. And so if you guys remember that oxygen is more electronegative than nitrogen, from our electronegativity chart, we can see that oxygen is more electronegative than nitrogen. And so oxygen is more likely to accept a negative charge. Therefore, when we illustrate the structure of nitrite, the negative charge is much more likely to be on the oxygen atom. Okay, we also need to remember the octet rule. And with these in mind, if you guys remember nitrite, the chemical formula for nitrite is NO2. Okay, and so so with that rules in mind, we can basically come up with the possible structures. So the possible Lewis structure. Possible Lewis structures of NO2 So let's draw the possible Lewis structures for them. And so first off, let's say we have N bonded with an oxygen, bonded with another oxygen. Okay. And so let's give the number of electrons that we need to assign to each atom. And in this case, for oxygen, we'll have 3 lone pairs, right? And the other 2 are bonding with nitrogen. And in this case, nitrogen will also have a pair. Okay, and in this case, oxygen has a charge of -1, -1, and +1, right? Since the charge of nitrate is -1, so we know that -1 and +1 will cancel out, and we still have a negative charge. Okay, so let's say this is structure A. Okay, now let's draw structure B. And let's say we can have another structure. Okay, so to draw out the next structure, what we can say is nitrogen is double bonded with an oxygen and double bonded with another oxygen here. Okay, so in this case, you can see oxygen can only form 2 bonds, right? So it formed 2 bonds, and so it would have 2 more lone pairs. And in this case, same for this. And nitrogen, as you guys know, it could form 3 bonds, but it doesn't really obey the octet rule. And so in this case, nitrogen, since it bonded all its electrons, basically, since nitrogen has 2 lone pairs, right? And in this case, it doesn't have any more electrons, right? So it makes this positive. And in this case, oxygen has a charge of 0. Okay, So our next possible structure would be, we have nitrogen, single bonded with an oxygen, and on this side we have another double bonded oxygen. Okay, so in this case, let's give out the lone pairs. In this case, nitrogen would have lone pairs, a pair of lone pairs, and then oxygen will have 3 on this end and 2 on this end. And so this makes this part of this terminal oxygen -1. This has a charge of 0, and this also has a charge of 0. Nitrogen has a charge of 0 because nitrogen normally can form 3 bonds, so it basically fulfilled its octet, you can say. And so in this case, nitrogen is 0. So basically, these are the 3 possible structures for nitrite. And of the 3 structures here, the most likely of them to exist is C. Since it has the negative charge on the electronegative oxygen atom and is structured with the simplest formal charge distribution, right? You can see that it can be A because you have too much formal charges, B because you don't have a formal charge of -1 basically, and C because the formal charge is, the negative charge is on the most electronegative atom, which is oxygen, and so the most correct one would be C. And so knowing this, we can add the formal charges to obtain the charge of the ion, which is, we know that it's -1, right? So therefore, NO2 has a charge of -1. Okay. Okay, so this is your answer. And so yeah, so exists is C, with which they have shown over here, and the solution here is. Okay, so our next question says, what is the charge of a sulfite? And so sulfite is formed by bonding a sulfur to ozone. So ozone, we know that ozone, it is so basically 3 oxygen atoms. It's O3. And so sulfite therefore is SO3. So the Lewis dot structure is shown on the figure below right here. So sulfur, as you can see, is double bonded to 1 oxygen atom. So let's draw out the structure. So the Lewis dot structure for sulfite is, so we have a sulfur in the middle. This is your central atom. You have, the sulfur could bond 4 bonds, right? So that's what 2 oxygen, and we have nothing, right? And so let's give out the lone pairs of these oxygens. In this case, this oxygen would have 3 lone pairs, and this one would just have 2, right? So this so what we have, so sulfur, as you can see, has 1 double bond to 1 oxygen, and the other ones are negative, so this would be negative, negative, and this is 0, since this oxygen over here doesn't, the double bonded oxygen does not have a charge. And so the results from this, the sulfite having a total charge of -2. Okay, we can see from our electronegativity chart that oxygen is more electronegative than sulfur. That's why your negative is on oxygen, right? And so this is the correct representation of sulfite with formal charge. And so therefore you can say that SO3 has a formal charge of 2. Sorry. And so this is what Tip said here. So the solution here is current. Okay, so our next question says, how do you convert millimeters to liters? So the prefix milli is used to denote a factor of 1,000. So you can write that milli means a factor of 1,000. And so if that is if I have a unit and a milliunit, they are separated by 10,000 units. And so basically 1 liter is 1,000 milliliters. So you can say 1,000 liters is equal to 1,000 milliliters. Okay, or and scientifically written 1.0 times 10 to the power 3 milliliters. Okay. Is 10 to the power, that's supposed to be 10 to the power 10 to the 3 milliliters, 1 liter. Oh, the solution. Okay, so our next question says, what is the strongest chemical bond? And so covalent bonds are the strongest. These bonds are formed through the sharing. So yeah, so covalent, however, I would also say ionic are the strongest, but in this case, so we can also say that covalent bonds are the strongest. Are the strongest. Strongest chemical bonds. Chemical bonds. Okay, and so these, as we know, that covalent bonds are formed by two nonmetals. Okay, so these are from basically your group 4 to 7 elements. Okay. So yeah, between these bonds are formed through the sharing of electrons between all, and it's also formed by two metals by sharing between two nonmetals, which fill in or completes the number of electrons in the valence shell of each atom, making it stable. And these bonds require high energy. So this is correct. Our next question says, draw the main Lewis structure of NOF. Draw non-bonding electrons using the dot notation and bonding electrons as a bond. And so as they stated here, the number of valence electrons present in the molecule NOF is 18. So the total number of valence electrons is equal to So we counted the total number of valence electrons of each of the atoms. So oxygen has a number of valence electrons, has 6 valence electrons. Nitrogen, 5 valence electrons. And fluorine has 7 valence electrons. And so once you add these two numbers, you would get 21, right? 6 plus 5 is 11, and then, 6 plus 7 is, 6 plus 5 is 11, plus 7 is, 18. Electrons in total. Okay. And so the Lewis structure of this, we would have, in this case, since we have three elements here, 3 atoms, we would have 3 bonds. And so in this 3 bonds, we would occupy 6 electrons, right? So 18 minus 6 will give you 12. So we have 12 valence electrons remaining. And so these will be, so count them as lone pairs. Okay. And so let's get started with drawing the structure. As you see, they said they have nitrogen as their central atom, fluorine, and oxygen. So in this case, nitrogen would have 2 lone pairs, as we know. Right, fluorine would have 6, and oxygen would have 2. So in this case, 2, 4, 6. In this case, we have 12. So what I mean by we have 6 lone pairs. Okay, and you can see this over here, where we have 2 lone pairs on oxygen, 1 lone pair on nitrogen, and 3 lone pairs on fluorine. So this is what they've got. So where the double bond on O, so it's supposed to be ON, and single bond on NF represents the bonding electron of the molecule, but the dots has to go first. Okay, so yeah, is correct. Okay, so our next question says, what is the molar mass of oxygen? Okay, so to find the molar mass of oxygen, this is given in the periodic table over here. So if we zoom in, so oxygen is in group 6, and you can see that it has, so this is your molar mass or the atomic mass, and in the top right corner here you can see this is your atomic number, and so the molar mass is basically 16.00 grams per mole. This is for 1 oxygen atom. However, we can relate molar mass is related to, so it's basically equal to your atomic mass, or your atomic mass. So this is, so the number down here is actually your atomic mass, but it's the same thing as saying your molar mass. So your atomic mass And we know how to calculate atomic mass. This is the number of protons plus your number of neutrons, right? And so your number of protons is equal to your atomic number. So for oxygen, it would be 8. And in most cases, for all elements, the number of protons is equal to the number of neutrons. So we can say this is also 8. And so you have an atomic mass of 16 AMU, or a molar mass of 16 grams. This is for one oxygen atom, okay? However, we know that oxygen is found as a diatomic molecule or gas, right? So we know that. So we can also say the molar mass of oxygen gas is equal to 2 times. So in this case, it would be 30. So natural occurring oxygen. However, this is the answer though. So 16 is your answer. And so this is. Okay, so next question says, how is pH determined given the molarity? So in other words, if you guys know, molarity is the same thing as saying concentration. It's also known as concentration. And so this is expressed in by moles per volume per liter. And so over here they have stated that pH, right, is a scale that determines how acidic or basic an aqueous solution is. So let me go. Where 7 is your neutral, this is 14. So this part is basic. This part is acidic. This is neutral. And so in comparison, where molarity or concentration is equivalent to the number of moles of a solute per liter of solution, which we just have. To understand how the pH level is determined given the molarity, we have to consider the following. So let's say, for example, they have over here. For example, a sample of nitric acid, which is HNO3, has a molarity of 0.0015 molar. So write this down. So the brackets here represent the concentration. HNO3 equal to 0.0015 molars. When it reacts with water, it will completely dissociate into hydronium and nitrate ions expressed in the chemical equation that is given. So we can write down the chemical equation, which is HNO3 plus H2O gives you your hydronium ions, which is H3O plus, and plus your nitrate ions, O3 negative. Okay, and so assuming there's 1 liter of solution, right? So in this case, your volume would be 1 liters. P is equal to 1 liter. It means that there is 0.015 moles per 1 liter of the solution. So because nitric acid is a strong acid, it will dissociate completely into your hydronium ions. So therefore, whatever the initial concentration of nitric acid is, so you can basically say, since HNO3 is a strong acid, the initial concentration the initial concentration of your nitric acid is equal to the concentration. Right, no, I should get this right. To the concentration of your hydronium, because it will completely dissociate into water. And so once you know the concentration of your H3O or your hydronium ions, the pH of the solution may be calculated. So we can basically calculate the pH now. So if you guys recall that pH is equal to negative log of the concentration of the hydronium ions. And so if you substitute the initial, so the concentration of your hydronium ions, 0.0015 molars, right? We do this, so this is log base 10. It would give you a pH of 2.82. So we know this is acidic, right? Because if you go back to our pH scale over here, we said anything from 0 to like 6.5 is acidic. And so you can see this is very, very acidic, right? And so basically the solution of the pH is 2.82. So this is basically the solution. And so you could also use an ice table, right, where you have the reactants and your products, and then you can use you can basically use this x squared to find so you basically solve for x and then you find the pH, which is basically the same way, but this would be more efficient because we're using a strong acid, right? And in this case, if you have a strong acid, it will completely dissociate into for acids, it will dissociate into hydronium ions. And so you can just use that concentration, the initial concentration, to find the pH. So this is And so our next question says, why is magnesium chloride named magnesium chloride and not magnesium dichloride? So this is a very good question because people will get confused when to have your prefixes and when to not. And so for magnesium chloride, let's first address what is this is formed of. It is formed by magnesium and chlorine, right? And so let's address these charges. This is negative, right? And we know when you form chemical formulas, you just crisscross the charges, and those become your subscripts. So so in this case, magnesium, we know magnesium. This is a metal because it's from group 2. So look at our periodic table here. This is a group 2, so this is your metals. These are your metals, and chlorine. This is a non-metal. Okay, so this is a group 7. It's a halogen. So it is in group 7, so it's negative. So it has a charge of -1. And so we can say that the bond between magnesium chloride, this is an ionic bond. And so we know the ionic bonds are comprised of a metal and a nonmetal. And so in cases of an ionic bond or an ionic compound, we do not use like prefixes where you don't really write the name of your last metal. You don't put "ide" or you don't put a prefix like mono, di, tri, or anything like that. Those are only for covalent bonds or when you're dealing with two nonmetals. So ionic bonds here. Ionic bonds do not use prefix. Only covalent bonds. So this is the answer. Right here, so and so this is why it is called magnesium chloride. This is why MgCl2 is called magnesium and not magnesium dichloride. Okay, so this is the main difference. The next question says, select the properties of an SN2 reaction mechanism. Okay, so an SN2 reaction is a stereospecific reaction, right? So let me write that down. A S2 reaction is a stereospecific reaction. And that is that different stereoisomers react to give different stereoisomers of the product. So um, different stereo produce different isomers, right? Of the product. And so it is also called a biomolecular at it is also a biomolecular at the rate determining step. We can also say it is a biomolecular at the rate determining step. The rate determining step. In which the overall rate depends on a step in which there is a collision between two separate molecules, right? That is why it is bimolecular. And so the mechanism has a rate of reaction which depends on the concentration of two first order reactants. So what we can say is that this is a mechanism um, mechanism of the rate depends on the concentration of the first two or of the two first order reactants. First order reactant. Okay, so this is why it is a second order reaction and it's governed by steric effect. So we can say the point that is a second order reaction and it is governed by steric effect and helped by and so from the given definition, basically, we can say from the given choices, we can say the answer is stereospecific. It is stereospecific. It is A. So the answer is A. So it's not B. It is C. So it's bimolecular at rate determining step. And let's see. It's not unimolecular. yeah, so second order weights are governed by steric. So this is correct. So it's A. So the answer is A, C, and A. Got so the solution here is okay. So our next question, sorry, says how do you write the balance equation for the combustion of propane? So as you guys recall, propane is where you have, so it's 3 carbons and it is 8 hydrogens, right? From a formula of 2 plus 2, where H is equal to 8, C is equal to N, right? And N is the number of carbons. So this is propane. And so we're asked to write a balance equation for combustion of propane. And so combustion is basically when it reacts with so the air reacts with oxygen. So we can say the balanced equation for the combustion of propane uh, propane is is so you have propane, which is a gas, usually H8 gas. This reacts with oxygen, and you form carbon dioxide and water. Okay, so now let's balance this equation. So in this case, we have 3 carbons on the left-hand side and 1 carbon on the right-hand side. So this is 3 carbons. So you write on the reactant side, we have 2 oxygens and we have 6 oxygens, 7 oxygens on this on the product side. And so to have 7 oxygens, we can just simply add. So we have 2, we can add a 5. So, or sorry, so in this case we have 7, and to make it an even number, so we can basically say this is 5. So we have 10, and this makes this. So we have 6, and so well we have 6, 7, and to have 10, we just have to add 4 onto this side, right? So we have 4 plus 6, which is 10, 10 oxygens on this side. We have 8 hydrogens and 8 hydrogens on the reactant side. So this is your balance equation for the combustion of propane. So yeah, so the last step would be to basically so the first step would be to balance the carbons. So the first step, balance the carbons. And then the second step would be to balance so the next step would basically to balance the hydrogens. The last would be to balance oxygen. Okay, and so this is the steps to to come up with a balanced equation for the combustion of propane. Okay. So yeah, so they have said to balance by balancing the carbon and then hydrogen and then oxygen. So the solution here is correct. Okay, so our next question says, how do you determine the molar mass of helium? So helium has a chemical symbol of Hd, and this is in your group 8. This is a noble gas, which means this is stable. And so from our periodic table over here, helium is a noble gas in group 8, and it has an atomic number of 2. And you can see the molar mass, or the atomic mass, is equal to 4.00 grams per mole. So the units for molar mass is grams per mole. Okay. So yeah, this is from your periodic table. So the solution is correct. Okay, so our next question says, what is the oxidation number of nitrogen and ammonia? Okay. So basically, there are a lot of rules when you are assigning oxidation numbers, and there aren't any rules for nitrogen, but we do have rules for hydrogen. So when it's a covalent components with nonmetals, hydrogen assigned the oxidation state of +1. So NH3, which is ammonia, right? And so in this case, from oxidation rules, when so when hydrogen is linked covalently, the oxidation state is the oxidation is +1. What we can say is that hydrogen in this case is +1, right? And or let's not write this yet. So the oxidation of N must balance the oxidation number of your hydrogen. And so what we can say here, so let's come up with an equation where, since we know hydrogen is 3, let's say let nitrogen, okay, let's solve for x. So we have x plus, so let's say N nitrogen plus hydrogen. In this case, we have 3 hydrogens and the oxidation is +1. And it would have to equal to 0, right? Since we're balancing out the equation. And so what we have is x plus 3 equal to 0, and we're just solving for x. So the 3 goes to the other side. We have x equal to -3. And so we can say, therefore, the oxidation number of nitrogen is -3. This is difficult, so solution here is correct. Okay, so my next question says, hydrogen chloride or hydrochloric is a polar molecule. How come the intermolecular forces among its molecules consist of London dispersion forces besides dipole-dipole interaction? And so since over here, so we'll say hydrogen chloride, this is a polar molecule. And so polar molecules exhibit dipole-dipole interaction due to the dipole moment created by the difference of electronegativity of the atoms present in the molecule. So our electronegativity chart, we can see chlorine has a electronegativity of 3, hydrogen is 2.1, so this makes it a polar. So if we say, so this makes alpha negative and this is positive. Okay. And so this is why this is polar. And this is why we have a dipole moment, but it doesn't mean that there's just a single intermolecular force. It is just that the dipole overcomes the other forces, so it is more significant than the other. And as you guys know, molecular compounds form a bond by sharing electrons with its neighboring, so it's a covalent bond. And the sharing of the electron causes the intermolecular force called the London dispersion force. Um, and so in general, all molecules have London dispersion forces. We know that London dispersion forces are relatively weak, but when combined, with a lot of London dispersion forces, the force is very strong. Okay, and so the last statement is that I just said that is said here is that just remember that there may exist other types of intermolecular force in the compound. It is just that there is a strong force than the other, so it is just the one being accounted for. Okay, and so this is correct. Okay, so our next question says, what is the net ionic equation of the reaction of iron chloride with sodium hydroxide? Include the faces of the species. Okay, so to get the net ionic equation, we must think of the reactants in terms of their significant anion or cation form. So for iron chloride, so FeCl2, we break this into the individual cations and anions. You would have Fe2 plus, right? And so for NaOH, just like sodium hydroxide, you would have sodium plus your OH, right? And so then we need to consider the solubility rules for all chlorides are soluble except for chlorides of silver, mercury, and lead. So we can all chlorides are soluble except with silver, mercury, and lead. And on the other hand, all hydroxides are insoluble except for hydroxides of barium and alkali metals, which include sodium. So, so, and all hydroxides are insoluble except with barium and alkali metals. Which includes sodium. Okay, so with this in mind, we can basically come up with an equation where we have iron, this is an aqueous, plus two hydroxide ions. How about alkaline? Hydroxides would give rise to iron hydroxide. So this would have two. Sorry, so this over here, it says, what is the net equation of the reaction of include the phases? So, since, what's it called? The hydroxide is insoluble with sodium, we don't really include it in the, equation. And chloride is, so chloride won't react. So if you react chloride with any of the other thing, with the other metal, it wouldn't produce. So in this case, you would just have this as your, and this is your solid, because it's insoluble except for when it's with in this case it would be a solid because your hydroxide is only soluble with barium and all the alkali metals. Okay, so the solution here is, and so basically that was the end of our session. If you like this Q&A, please subscribe to the OneClass channel and be updated whenever we upload a new video. And to do that, press the bell icon to get notified. And also, if anyone needs one-on-one tutoring sessions or has their personal questions to ask related to any of the topics, follow the links in the description box to ask your questions. And other than that, I'm Shanjida, and I hope to see you guys soon. Bye-bye.